there any questions over any of the assignments thus far? Any questions over any of the homework assignments? Now, the first thing we're looking at today is the rational zeros theorem. We're looking over the rational zeros theorem today. And the rational zeros theorem gives us all the possible rational solutions of any polynomial function. And it'll come in the form of plus or minus p over q, where p is the factors of the constant term and q is the factors of the leading coefficient. P over q. And this gives us all the possible rational zeros. Some of the rational zeros that it'll give us won't be possible or won't work, but most to all of them could work. Because it gives us all the ones that could work, but it doesn't mean that they will. So the main thing I would get down is so what we want to do for this first one here, we do want to find the possible rational zeros. So our plus or minus p over q, where p is the factors of the constant term and q is the factors of the leading coefficient. So the constant term in this case is what? 20. Constant term is the number without a variable. So we're finding the factors of 20. So we would have 1 and 20. Then we'd have 2 and 3 doesn't work, but 4 and 5 do. So all the factors of 20 are 1, 2, 4, 5, 10, and 20. Now what's the leading coefficient for this here? Because the leading coefficient is the number in front of the variable with the biggest exponent, and that number is 1. Any questions on how we found the factors of the leading coefficient and the factors of the constant term? Now to find the possible rational zeros is we take all the factors of p and divide them by all the factors of q. And I always start with the first value of q, which is normally going to be 1. So what we can do is 1 divided by 1 is 1. Then we'll do 2 divided by 1, which is plus or minus 2. Then we can do 4 divided by 1, which is plus or minus 4. Then we can do 5 divided by 1, which is plus or minus 5. Then we can do the next one, 10 divided by 1, which is plus or minus 10. And lastly, 20 divided by 1 is plus or minus 20. So all of these here are the possible rational zeros, but we're only going to have 3 zeros. There's only 3 values of x that will work for this here. Now, realistically, if I can find at least 1 for this here, it will reduce it from, if I find at least 1, I can use synthetic division to reduce it from a degree 3 down to a degree 2. Then we can use quadratic formula from there. Now, you don't have to write this next part down, because what we can do by the pure math definition, the way that we would do this is set this up with synthetic division. Because if the remainder is 0, then it's a solution, yes? Well, what's our first number we have here? So I do 1 times 1, which is negative 8 plus 1 is 1 times negative 7. 11 plus negative 7 is 4. 1 times 4 is 4, which gives us So is 1 a solution? No. So I'll grab the eraser for this here and erase all this here. Okay? 1 didn't work, but then I would try it with -1. If that doesn't work, I would try 2, then -2, 3, -3, 4, -4, 5, -5, 10, -10, and 20, -20, going through and seeing which one would work. Is the pure math way to do this. Or we can grab the graphing calculator, clear all that out, clear that out, say y equals. We have x to the third minus 8x squared. Is it 11x? I'm trying to remember what the next one. 11x plus 20. And we can hit graph. It does cross in 3 places, yes? Where does it cross at? -1, when x is -1, y is 0. When x is 4, y is 0. When x is 5, y is 0. So our 3 values are -1, 4, and 5. So the solutions for this here, x is equal to -1, 4, and 5. Those are our 3 solutions. Are all 3 of those listed as our possible rational zeros? That's it. Because if we had tried -1, -1 times 1 is -1. -8 plus -1 is? -1 times -9 is 9. 11 plus 9 is 20. -1 times 20 is -20, which indeed does give us. I can do it again, this time with 4. 1. 1 times 4 is 4. -9 plus 4 is -5. 5 times -5 times 4 is -20, which gives us 0. And just for kicks, I can do it one more time with 5. 5 times 1 is 5. 5 plus 5 is 0. I get another remainder of 0. Well, that just tells me I have 1 left. I have a constant 1. That doesn't mean anything. So those are our solutions. Did I really have to do any of the synthetic division? No. The graphing calculator gave us all the answers. Questions on this here? I feel like y'all are getting the hang of this, yes? For the most part. I'm going to skip this one here and this one, because these two, if we wanted to find the solutions, x cubed minus 5x squared minus 2x plus 24. X cubed 5x squared, what's it, 24x? Okay. Does that mean if we wanted to, we can hit minus, graph, -2, 3, and 4. We have them. And we would see that those are listed. So these here, we can graph them and get the solutions. And a lot of these higher degree polynomial functions, that's where I would start. I would start with graphing. Now, especially if the leading coefficient's 1, that's where I would start with, is graphing. Because with any of those, if we can find at least n-2 number of solutions, the degree -2 number of solutions, we can get it down to a quadratic and then use the quadratic formula from there. Now, especially if, so this here, let's go on and graph this first. So y equals 10x to the 4th minus x to the 3rd. I think it's plus squared Does this intersect at nice numbers? No. Okay. Now these here is where, and this here is where the rational zeros really does come into play and is very helpful. So if we look at the rational zeros, our plus or minus p over q, I would give yourself enough room. I'd write this as far to the left on that page as you can, because we're going to have several. Now the factors of p and factors of q isn't going to take up too much space. Now factors of q this time is not going to be just 1, because we're looking at the factors of 10. So we will have 1 and 10, but we also have 2 and 5. So we have 4 different factors for 10. Now for p, we have 1 and 12. We also have 2 and then we have 3 and 4. Now when you write those factors out, if you realize you put way too much room, it's very easy to just erase and move everything over. Now, when we do this here, if you've noticed, well, we start off with q being 1. I like doing this just because if we do have some that repeat, it's easier to see them if we start off with q being 1 and moving up from there. Well, really, when we divide anything by 1, we just get with what we started with. So really, I can go through and list all the values of p. Because when we divide p by 1, we just get p back. So 1 divided by 1 is going to be 1. Same with 2, 3, 4, 6, and 12. Really doesn't give us much. Questions on this so far? Now this is where it changed, and this is why I kind of wanted to move to this one here. Because now I'm going to move over to a q value of 2. So we're going to do 1 divided by 2. There's going to be plus or minus 1/2. Then we can move to the next one. 2 divided by 2 is 1. Do we have 1 listed? We're not going to list it twice. If it's already listed, we'll keep it as that 1 there. 3 divided by 2 is 1.5 or 3/2. I'll leave them. I kind of tend to leave them as mixed numbers. So we have 3/2. Then we go to the next one. 4 divided by 2 is, we have it. Next one, 6 divided by 2 is, we have it. And 12 divided by 2 is, we have it. Okay. And really, the ones that we have had a common factor between p and q. Well, we looked at the next value of q. The next value of q is 5. None of our factors of p have a common factor of 5. So we'll start off with 1 divided by 5, which will be plus or minus 1/5. Then we have plus or minus 2/5. And we do 3 divided by 5, plus or minus 3/5. Then you move to the next one, 4 divided by 5, plus or minus. Then we move to the next one, 6 divided by 5 is 6/5. And lastly, 12 divided by 5. All right. Let's go with this color. Now the last number that we have for q is 10. So we'll start off with 1 divided by 10 is plus or minus 1/10. So we'll always have 1 over the value of q. That's going to show up every time. It won't reduce. It won't simplify. Now when we look at the next one, 2 over 10 is what? 1/5. Do we have 1/5? Yes. So we move on to the next one, 3 divided by 10. 3/10. 4 divided by 10 is 2/5. We do have it. The next one, 6 divided by 10 is 3/5. We have it. And lastly, 12 divided by 10 is 6/5. And we have it. Yes? So all of these here are the possible rational zeros. How many of these values would we like to have work? 4. Because if we have 4, and especially if 4 showed up and they were one of these, that would be very nice. because that means they're on the x-axis. I can find them easily. Now, out of all these here, if we counted them all up, we have 32 possible rational zeros. And if we did this by the method I showed you all at the beginning, we would have to try synthetic division 20 or 32 different times. And at most, 4 are going to work. But again, as I said, this here is the list of possible rational zeros. That means they have to be rational. The problem we ended off yesterday, we found the solution for it was 0, 2, negative 2. You all remember what the other two values were? 2, negative 2. Then we have the square root of 3 and negative square root of 3. Are the square root of 3 and square root of negative, or negative square root of 3, are they rational? No, they're irrational, yes? So it is possible for this to have irrational solutions. Will those solutions be listed here? No, because this is only possible rational zeros. So it could be, if they were very mean, none of these could work. It could mean that all 4 solutions are irrational or complex, or a combination of those two. But one thing that is nice about this, in our graph, because we graphed it, yes? So I do have 4 locations that we do have possible points. We can use this with the rational zeros to narrow down our list. As we can see here, does any of these 4 places where it crosses the x-axis, does it cross at a whole number or a natural number? So when you look at the list, because one of our choices was positive 1, negative 1, yes? Does either one of those give us a value of 0? No, we also had 2 and negative 2, 3 and negative 3, 4 and negative 4, 6, negative 6, 12 doesn't work. So what can I say about all of these whole numbers here? Natural numbers. Nope, 1, 2. None of these are solutions, which that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It means I don't have 32 anymore. I now have 20. I didn't even have to check it. I just looked at the graph. Those are gone. So that leaves us with all of these fractions. Now looking at the graph, is there one of these points that looks like it could line up with one of our fractions? Negative 1/2. So what we can do is, using the graph and this here, is I can set up synthetic division and put negative 1/2 in the cubbyhole, because that is one of our possible rational zeros. Now across the top we'll have 10 for x to the 4th, negative 11 for x cubed, negative 42 for x squared, 7 and 12. Then we bring down the 10. Now with any of this here, I have a feeling at this point you are using the calculator a decent bit with some of the synthetic divisions. I mean, for the most part, most of the stuff we've done with synthetic division hasn't been too bad. Here, we're going to do negative 1/2 times 10. Well, half of 10 is 5, and this is going to be negative. Negative 11 plus negative 5 is, make sure I did that right, yep, negative 16. Now we're going to do 1/2 of negative 16. Well, negative and negative makes a positive, and half of 16 is 8. Well, negative 42 plus 8 is, make sure, 2, 6, negative 34, isn't it? Yeah, I'm questioning myself. I've already did the wrong operation this morning with pre-calculus, so just making sure. Negative 1/2 times negative 34 is going to be 17, because negative and negative make a positive. Cut 34 in half, we get 17. 17 plus 7 is 24. This is looking very promising. Negative 1/2 of 24. Well, it's going to be negative 12. 12 plus negative 12 is? So is negative 1/2 a solution? Now, if we were doing this purely mathematically and we just picked negative 1/2 and tried it, okay, it worked. It doesn't mean that it couldn't work again. But looking at the graph, we know at negative 1/2 it does cross it, yes? Which means it has to appear an odd number of times, and most likely negative 1/2 is not going to appear 3 times. Because we also have 3 other places it crosses for our solution, so that's not going to work. So we found one. Now we need to find 3 others. I would think positive 1/2 would probably not work because on the positive side, it's kind of a little bit too big, yes? Now we can try 4/5. Now I'm going to write this down. I would not advise y'all to write this down, mainly because the amount of space that y'all have for this problem is limited and you're at the bottom of the page, yes? So I want to show you guys this just so that y'all can see, especially as you're working these. 10. We can do 4/5 times 10. And we could do this in a calculator or by hand. 10 divided by 5 is 2. 4 times 2 is 8. Negative 16 plus 8 is negative 8. That's fine. 4/5 times negative 8 is negative 32/5. Is there any way that 32/5 is going to somehow reduce out? Probably not, because when we add it to negative 34, we're still going to have fifths. We multiply it by 4/5. Now we're going to have 25/5, or instead of having fifths, now we have 25ths. And it's just going to get worse and worse. Now in the graphing calculator, if we go second calculate, or second trace enter. So I'm going to do it again, second trace. If we look at that top value, top point, it says value, yes? This lets us, if we hit enter, plug in a value of x for this function. So if I do 4/5, 4 divided by 5, enter. It tells me the y value is negative 10.816. What y values are we looking for? 0, yes? So is 4/5 a solution? No. So I could have done this before I started the long division or synthetic division to see if it's going to be 0. It tells me it's not. So what other value could work? So we just found out positive 4/5 does not work. Well, as we do see, because that 1 between 0 and 1 is close to 1. So 4/5 did not work. So let's see here, which other ones are close to 1? Well, positive 1/2 is not close to 1. 3/2 is too big. 1/5, 2/5, I'd say those are a little too small. 3/5 might work. Well, 6/5 is close to 1, but it's on the wrong side because it's going to be bigger. 12/5 is way too big. That's bigger than 2. 1/10 and 3/10 are too small, yes? So what's ones that possibly could work? Pause it one more time. I just heard a bunch of numbers. Because right, so let's try the 3/5 fourth, or negative 4/5 is what you said first, yes? So we can try it. So calculate trace value, negative 4/5. Oddly, I think it gave us close to the exact same value, but it didn't give us 0. So nothing gained, nothing lost. But we can try negative 3/5. We do see where it's at, but it's not 0. So let's try the last one. 3/5. It gives us a value of 0. And that's helpful because now we can come over here, instead of 4/5, we can replace this with a 3. Now we can do this one here. Erase all that. Picture. There we go. So we can say 3/5 times 10. And I mean, you can do all this multiplication addition in the calculator. And it's actually not that bad. Because I can show you guys this here. So quit. So we can say 3 alpha y equals enter fifths times 10. Well, delete, try again. Times is 6. Then we have plus negative 16 is and then we're going to do 3/5 times negative 10. Well, it's going to be negative 6. And we could repeat that process because we could do times 3/5. And I mean, you can do this in the yellow calculator a lot faster than you can in the graphing calculator. Add straight down is negative 40. 3/5 times negative 40. Negative 24. And 24 plus negative 24 is 0. Questions on this here? Could those other two solutions be rational numbers? Yes. Could they be irrational numbers? Yes. Could they be complex? No. And the reason we know they're not complex is because we see that they do. There are two definite places where they cross the x-axis, yes? If they were complex, we wouldn't have those. Complex numbers do not cross the x-axis. But we still, because even if I take negative 1/2 off, because we know we already have it, it's fine. And we took off positive and negative 3/5. We took off the negative 4/5. I still have a good number of solutions here that could work, yes? But what's the degree of the polynomial that we have now? Because we started out with 4, yes? So I'm going to fill them in, because here, this here is a 4th degree. Because this is x, x squared, x cubed, x to the 4th. This next one here, x, x squared, x cubed, I reduced it by 1, yes? And when we divide it again, constant term, x, x squared. Now I have a quadratic. One method that always works for quadratics is negative b plus or minus the square root of b squared minus 4ac all over 2a. This one will work for any and all quadratics. And as we saw the other day, so before I jump to that next thought, so we can use this here. We could go through and try all the rest of the rational zeros to see if they work. They could or they couldn't. Or because we already have it to degree 2, I can use this formula here and solve. This is guaranteed to work. Checking the other zeros is not guaranteed. So we have this here. So we can say that our quadratic's 10x squared minus 10x minus 40 is equal to 0. Now, I did show y'all, especially graphing yesterday, that if there's a constant term that's just a number, we can remove it. It still gives us the same equation, just a little bit easier to work with. Here, there's a greatest common factor of what? 10. I'd divide the whole thing by 10. because that'll give us x squared minus x minus 4 is equal to 0. Because if I plugged 10 in for a for the denominator, we'd be looking at 20. If I plug 1 in, we're just looking at 2. I would have to get rid of that factor of 10. Already did. Now we can just plug this in. So negative b, well, b is -1. Square root of b squared minus 4. Well, a is 1. C is -2 over 2 times 1. Now, at this point here, we can simplify. Negative 1 is 1. 2 times 1 in the denominator is 2. Now, personally, again, as when we went over this the first time, I don't type the radical in quite yet. I plug everything inside the radical into the calculator. So -1 squared minus 4 times 1 times, well, times -4, and hit enter. So we squared to 17. And we can plug this into the yellow calculator, our 30xs, and if we plug in the square root of 17, it's going to tell us that it's the square root of 17. Square root of 17 doesn't simplify. And how many solutions do we have here? 2. So I have 1, 2 here, -1/2, and those are all of our possible, not possible, those are all of our zeros. Those are all of our solutions. And it's kind of a good thing we went on and did the quadratic formula for this, because it also means none of the other solutions, our rational zeros, would have worked. Because 1 plus or minus the square root of 17 over 2 is irrational, it wouldn't have showed up. Questions on this here? Questions on anything we've done so far? So we'll stop there for today. We'll finish this up